Morning, class. Wow, that was disappointing. I even saved the good mornings so that when I hit, I don't know if anybody realized, but I hadn't greeted you yet. I was waiting for the video to start so it would sound great, but no, never mind. It's okay. It's all right. Hopes and dreams, front yard, gasoline, matches, gotcha. All right, so this section is called Nth Roots and Rational Exponents, and our authors of our textbook believe that you have mastered and definitely remember all of the exponent rules that you learned in Algebra 1. Exactly. So, I have decided to start these notes with reviewing the exponent rules that you need to know from Algebra 1. First one is basically combining like terms. If you are adding and subtracting things with the same base, all you're supposed to do is combine like terms. Bless you. Like terms require the same base and the same exponent. So this really says I have 2 objects. I'm adding 6 more of the same objects. Like 2 cookies plus 6 cookies gets me 8 cookies. Nobody spoke, so I'll just say it. 8 cookies. There it is. So nothing changes with exponents when you're adding and subtracting objects. It's just going to change the number of those objects. But the moment you start doing any other operation besides addition and subtraction, exponents get to be altered. Yes?
What if they're like different number exponents?
Then they're like terms. If they have to have the same base and the same exponent. So like what is x plus x squared? I don't know, it's x plus x squared because they're not like terms. You can't add them. No, you just leave a plus sign in between them because you can't do anything about it. Now you can multiply though. You can multiply and divide anything you want to, right? Like this example. You'll see that my x's don't have the same exponent. They're no longer like terms, but who cares because we're not adding and subtracting, we're multiplying. When we multiply things with the same base, does anybody remember what you do with your exponents? You add them, of course you do. That's why x times x gets you x squared, because you're adding the power of 1 and 1. So we're going to add the exponents. I wonder if we can hear their conversation about the video games on my video. Anyway, 2 times 3 is 6, and you've already said to add the exponents. So we get this 5 plus 4 going on, and we have 6x to the 9th. There it is. If multiplying numbers with the same base makes us add our exponents, what do you think dividing numbers with the same base does? Subtract your exponents, yes. But I am going to say, yes, subtract your exponents, but make sure your results have positive exponents. Well, 2 and 8 don't have exponents, but they're just numbers, so you reduce the 2 and the 8. 2 over 8 reduces to 1 over 4. The trick to this whole subtracting exponents thing is to ask yourself, well, where were there more of them, on the top or bottom? You guys can tell me. The top. So since there's more of them on the top, what we're going to do is we're going to say that's where they'll end up in the end. And then we subtract. So we get x to the 7th over 4. Just to show you specifically what I was just talking about, I'm going to swap the x's, their exponents, okay? If I'd given you 2x to the 3rd over 8x to the 7th, the 2 and the 4 still reduce the same way. That's still going to give me a 1 over 4, like that. And we are still going to subtract our exponents, but we're going to make sure that our exponents stay positive. So I'm going to say, oh, I didn't mean to write a 7 there. I meant to write a 10. But it doesn't matter. It's already written. Where are there more x's, the top or bottom? The bottom. So what you do is you put the x's there, and then you subtract the exponents. So once you've decided where they're going to be, it's just going to be bigger exponent minus smaller exponent. You see there's nothing on top right now. There has to be something there. So what's there? Not an x, a 1. So even though it is just, yeah, subtract the exponents, there's a little bit more to the rule, and it involves you saying, well, where's there more of them? And the reason why we do the whole where is there more of them is because if we can avoid negative exponents, we will avoid negative exponents because that creates more work for you. Alrighty, let's see who remembers. Things raised to the power of 0. What is that going to give you? Not 0. 1. And that's true for all numbers except for 0. Yes?
Why does it get 1?
Ah, what a great question. Why, instead of just accepting it as a truth? You know why she asked? Because she's a nerd. All right, let's see. No, it's a great question. It's a fantastic question. And I'm always ready for it. Let me use powers of 2. Okay, so 2 raised to the power of things. What is 2 to the third? It's 8. What's 2 to the 2? 4. What's 2 to the 1? 2. Let me ask you, what am I doing to this number every time? So every time the exponent decreased by 1, I divided by 2, right? What's it going to give me? 1/2. So, but was bonus knowledge. I just reminded you what negative exponents do also. But that is why everything to the 0 power except for the number 0 gets us a 1. Yes, Jared? 0 to the 0 is worse than undefined. In mathematics, we say it's indeterminate. There's a lot of things in mathematics that we say are indeterminate, and they usually involve zeros and infinities. So like, what's infinity plus infinity? The answer is indeterminate. What's infinity raised to the infinity? Indeterminate. What's infinity to the 0? Indeterminate. 0 to the infinity? Indeterminate. So there's a lot of things where we go like, common sense tells you 0 to the infinity should be 0, right? Oh, but the problem is infinity is not a number, so you can't do that. So in mathematics, when those kinds of things occur, we go, that's indeterminate, and we have to manipulate it until the infinities and things like that disappear. But that's why I said don't try to do 0 to the 0. That's a upper level calculus concept, and you figure out how it gets handled then. Alrighty, what about raising a power to a power? Multiply exponents, good. You know what's neat about multiplication? Order doesn't matter. So I could say that this is x to the 3 times 4, which is x to the 4 times 3, which means it could have been written as x to the 4th to the 3rd. Look at that. I could switch the order of the exponents if I want to, because the order of multiplication doesn't matter. Either way, we're going to get x to the 12th. But this idea of interchanging exponents like this is a pretty useful tool for us a little bit further down the road. Pretty useful. In this lesson, actually. It won't happen today, but tomorrow when we continue the lesson. I'm going to say that again. We're not finishing the lesson today. This was designed to be a 2-day lesson. All right? So I need to make sure that you're good at the Algebra 1 before I ask you to do the Algebra 2. This raising parentheses to a power, I want to alter what that says. I don't want to say raising parentheses to a power. I want to say raising products or quotients to a power. See, this one is a product inside those parentheses. 2 times some stuff. There's a multiplication dot between that 2 and that x to the 5th. That's what I tried to just show with my blue pen there, but it's kind of tough. Anyway, when you raise a product or a quotient to a power, I don't know if you caught that, but what I'm saying is it doesn't matter if inside these parentheses was multiplication or a fraction bar. The rule is still going to hold true. Does anybody think they remember what you're supposed to do? Nope. You think, got it? Jared, what do you think? You're going to give the power to every term on the inside. Yes? And that's exactly what would happen as a net result. Yep. So because there's a product or quotient in here, all of the parts inside get this exponent. And I'm glad you said give it to instead of saying the word that a lot of students would have said, and they would have said distribute. And then I'd have to correct them and go, no, it's not distribution, because distribution is specifically used when you are multiplying a constant or something to a binomial, trinomial, things that are held together with pluses and minuses. These are not held together with pluses and minuses. This is either a product or a quotient. So we could say give it to everything. We could say apply it to everything. The point is all of the objects get that exponent. So I'm going to write it as 2 to the 3rd times x to the 5th to the 3rd. And like Gabriel said, 2 to the 3rd is 8. And here we have power to a power situation, which we just talked about. So we multiply it and get x to the 15th. There it is. So I guess the resulting rule, raising products or quotients to a power, the rule is give exponent to all parts. And then if there's other rules that have to take place, then other rules have to take place. And the last bit of your Algebra 1 review for exponent rules is talking about negative exponents. And like I said, on this little sheet of paper, we had a negative exponent. What we saw was 2 to the negative 1 is equal to 1/2. So what is it that we think negative exponents do to things? What is it that we think negative exponents do, Daniel? What if it was already in the denominator? So, because they couldn't hear you on the video, so he says it moves it to the denominator. In this specific case, it did move it to the denominator. What if it was already in the denominator, had a negative exponent? Then it moves to the numerator. And the reason why we're moving it is because we're trying to get a positive exponent, right? So what can I write as a generality? If something has a negative exponent, in general, you say, we're not, okay, and now you said the word that I was hoping to hear so that I could correct it and make sure we never hear it again. We don't want to say that we flipped it. What we want to say is that we move things with negative exponents across their fraction bar to make the exponent positive. And Daniel, the reason why I'm going to make the distinction here is, does this 2 have a negative exponent? No, it doesn't. And that's why we can't use the word flip here. Because if you flip this over, you get 1 over 2x to the 3rd. But the 2 does not have a negative exponent, so this 2 does not move. So instead what we'll say is negative exponent, move object across fraction bar and make exponent positive. What was after green? Orange. All right. Don't tell my wife, she'll be mad. Orange and green don't go together. The 2 doesn't have a negative exponent. By the way, here's the fraction bar that we're talking about. The 2 doesn't have a negative exponent. That means the 2 gets to stay right where it is, on the top of this fraction. But the x did have a negative exponent, so it has to go to the bottom, and then its exponent is positive. And there we go. If you're not worried about negative exponents, and you instantly know how to handle them every single time, then this question that I was doing up here with you, where I was like, well, decide where they're going to be, on the top or the bottom. You don't even have to do that. Because what you could have done was you could have said, oh, when I subtract, I'm going to have x to the negative 4. But I can't have negative exponents, so move it to the bottom of its fraction to get x to the positive 4. I think it's easier to go, where's there more of them, top or bottom? Okay, do it there and do the subtraction. That way you always end up with a positive exponent. But that's just because if I can avoid the negative exponents, I do. This one. Does the 2 have a negative exponent? No, it doesn't. That means the 2 stays on top of this fraction bar. Does the x have a negative exponent? Sure does. Move it to the bottom then. And when it goes to the bottom, its exponent turns positive because you cross the fraction bar. Does the y have a negative exponent? Yeah, it does. That means it can't stay there either. It gets to move to the top. And now its exponent is positive. And you know what else? There are times, times, where it's beneficial to go, you know what, I don't want that variable in the bottom of the fraction bar. I'm going to go ahead and move it to the top, and I'll just make the exponent negative. Sometimes it's very beneficial to move an exponent, or not to move an exponent, move an object across the fraction bar and make the exponent negative. You'll see times where that's very useful to us very, very soon. Not this chapter, unfortunately, but it will come up after the holiday break. And I know it's not in here, but I do want to show you a very special case of a negative exponent. And it's not even a special case, it's actually a combination of 2 different rules that are in this box. What if a quotient has a negative exponent? We already talked about the fact that when you have a product or a quotient inside the parentheses, all the parts get the exponent, right? So that would mean that I would have a 2 to the negative 1 on the top. And on the bottom, I have a power to a power. So I have to multiply. But then what we just talked about was anything with a negative exponent is going to move across the fraction bar to become a positive exponent. That means the 2 goes to the bottom and gets a power of 1. The x comes to the top and gets a power of 3. Now tell me, what was the net result? That is the only time that you can use the word flip. Because yes, if you have a fraction, a quotient, that the whole thing has a negative exponent, then the fraction flips over. And what happened is the outside exponent becomes positive. You can imagine this whole thing has a power of 1 now. And the reason why I said it like that is because if this was a negative 2 out here, I could have just flipped the fraction over. Now the power of 2 is positive, and then just apply the power of 2 that's positive to all the crap on the inside. So it's not even that it's so special, it's that it's a combination of the rules. But basically, anytime I see a fraction where the whole fraction is a negative exponent, yes, I flip the fraction over, and then I make that outside exponent positive. It does not affect the inside exponents, only the outside one. Cool with that? Like 2 people nodded. Great. So happy that I've got everybody's attention. Anyway, that is your Algebra 1 review of exponent rules. Now, let's talk about powers of numbers. We've already dealt with reducing square roots this year. So I told you you really need to know your powers of 2 and some multiples of them, right? not your powers of 2, excuse me, your exponents of 2. Your 2 squared, 3 squared, 4 squared, 5 squared, yada, yada, yada. But you know what? The power of 2 is not the only things that you want to just know. You also want to know some perfect third powers. We call them perfect cubes. You want to know some perfect fourth powers. We call them, if you care, quartics. Perfect quartics. We'll just say fourth powers. And it might be beneficial to know 2 and only 2 perfect fifth powers. Alrighty, let's talk about 2 to the third. What is 2 to the third power? 8, because it's 2 times 2 times 2, 8. What is 3 to the third power? 27, because it's 3 times 3 times 3, which is 9 times 3, 27. Ooh, 4 to the third power, 4 times 4 times 4. 64, because it's 16 times 4, 64. Think money. 5 to the third power. 5 times 5 times 5. 125. Because if you had 5 quarters, you'd have $1.25. Because if you had 5 quarters, you'd have $1.25. 6 to the third. Woo! It's 6 times 6, which is 36, and 36 times 6, 216. The reason why we know it's 216 is because 30 times 6 is 180. 6 times 6 is 36. 180 plus 36 gets me 216. And lastly, 7 to the third is a big number, but it's 7 times 7, which is 49 times 7. 49 times 7. Okay, well, 40 times 7 is 280. And 9 times 7 is 63. 280 and 63. 343. Look, I'm going to be real with you. You must know the first 5 perfect cubes. And that includes 1 to the third. You must know those. You just have to. These 2 are extra money. You know what I mean? It's like, why wouldn't you want to know a little bit more? You got to know those. See what's happening with this table? But these numbers actually, they come up pretty often also. Just like we were doing with our squares and we were trying to reduce, if you can't instantly see a big perfect cube that goes into something, by all means, look for smaller ones that go in and just do lots of splits. It still works. It's just more effort than I want you to give. How about 2 to the fourth power? It's 16. I like fourth powers. They're fun. The reason why is because the fourth power, hey, isn't it true that when you multiply 2 numbers with the same base, you just add their exponents? It's true, right? Oh, okay. So if I wanted to, I could say that x to the fourth was just x squared times x squared, right? So if I said what's 2 to the fourth, and you didn't instantly know, you could just see it as 2 squared times 2 squared, and 2 squared is 4. This is just 4 times 4, which is 16. And we can do the same thing with 3 to the fourth power. 3 times 3 is? 3 times 3 is? 9, okay, and 9 times 9 is? 81. And this one right here, if you're one of the people that actually bothered memorizing the perfect squares like I asked you to, when you want to say 4 to the fourth power, you go, what's 4 times 4? What's 4 times 4? What's 16 times 16?
196.
Close. It does end in a 6. 256. Okay. Check this out. Times 2, times 2. Hope it's obvious that x with 2 to the fifth is 32. Because it's just 16 times 2. And the last one that I would say, just kind of know it because it shows up often, is what 3 to the 5th power is, which is basically 81 times 3. You don't know 81 times 3? Fine. What's 8 times 3? 8 times 3 is 24. And 1 times 3? There you go. So I would know those numbers, super useful to you. Now, what used to be its own box, but is now not its own box, is roots of variables with exponents. And it's actually roots of anything with exponents. How do we do roots when something has an exponent on it? That's the real question. You divide the roots, you divide the exponents by the root index. Mr. M, what's the root index? That's what kind of root is it? Is it a square root, third root, fourth root, fifth root? That number is called the index of the root. So for example, actually let's put the official rule on here. The official rule. There's the official rule. You divide the exponent by the root index. What kind of root was it? For example, what's the root index of a square root? It's a 2. It's the second root. That's why it cancels the second power. The other part says remainders are stuck inside. What do I mean by that? I mean like this. This one's a trap. A lot of students will want to say that it's x squared. It's not. Because they're looking at that and they're going, oh, 2 to the third is 8. No, you can't do that because that's an exponent. If I said, what's the cube root of 8, you would say 2. But this isn't cube root of 8. This is cube root of something raised to the 8th power. Can I divide 8 by 3 without a denominator? Or not a denominator, what's wrong with me? Without a remainder? No, there's going to be a remainder. What number could I have divided by 3 and not get a remainder? The 6. So what you do is the same thing we were doing before. You split it into something that works and something that doesn't work. You've got a cube root, the 6 with a remainder of 2. This will be stuck inside. Why, Master Rem? Because its exponent is smaller than the root index. You can't divide it. But what will happen is this x to the 6th gets to come out. It gets liberated. And when it comes out, you divide its exponent by the root index. And 6 divided by 3 is 2. But this thing is stuck inside the cube root. See, the remainders get left inside. How do you feel about that? Good? Okay. So everybody just trusts that what I said works. Okay. All right. Nobody cares why. All right. It's fine. First period, someone asked me why. So I showed them. Do you care? Yeah? What do square roots cancel? What kind of power? The 2 power. Square roots are used to cancel perfect squares, right? Okay. So what I'm going to do for this one is I'm going to break this x to the 8th into a whole bunch of x squares. Because we know that's what square roots cancel. When you multiply two numbers with the same base, you add their exponents. Every one of those is a perfect square, isn't it? Okay. So what's the square root of the first x squared? X. What about the next x squared? How about the third one? And the fourth one? Oh, guess what x times x times x times x is? This is a shortcut. It works because each root type wants to cancel that exponent. So a square root wants to cancel the second power. The third root wants to cancel the third power. So I could have said this is x to the third times x to the third. And the cube root of x to the third is x. Two of them would have come out sitting next to each other, and that's why it would have been x squared. This division thing is a shortcut. But this is why it works. So here we're just going to be simplifying some radicals. Mr. M, some have symbols in front of them. Why? Because I wanted to. Just like if I had wanted to put a number in front of it. Who cares? It just means multiply by whatever's out there. It's not a big deal. So the first one, there's actually a plus or minus in front of it because who cares? That just means all my results are going to have a plus or minus in front of them. Whatever. Is 25 a perfect square? Yay! And x to the fourth, can I divide that 4 by the root index without a remainder? Yes, yay, that means it's also a perfect square. So we're just going to write plus or minus, because that was already there, the square root of 25. And when the x comes out, what will its exponent be? 2. Is that because the square root of 4 is 2? No, it's because 4 divided by 2 is 2. It was division. There. Nothing left inside, so we don't have a radical. I like example B because there's two completely different, completely correct ways of handling it. And it doesn't matter which one you choose. Someone want to tell me how they would like to proceed with B? Anybody? All right, Gavin, what do you got? What would you do? Okay, so because more than likely I couldn't hear on the video, Gavin basically said, use the rule that says when a product has an exponent, you apply the exponent to all the things on the inside. You notice that you're going to have a power to a power situation in there, so you multiplied and said 24. So what you were saying is you would have written it as, here's your negative sign, and then you would have gotten y to the 24th, because power to a power, and z to the 12th. How would you have proceeded from there? So you said you would have divided the exponents by 2 because that's the root index. So you would have gotten negative y to the 12th, z to the 6th. A perfect answer. But it's not the only way to get that perfect answer. It is the way that the volunteer from period 1 also said. Anybody see the other way of getting there? No? Then I'll do it up here in a different color. I know they look the same, but they're not. One's orange and one is red. I did that in red. I'll do the other version in orange. We said when something has an exponent, you divide the exponent by the root index, right? And that would get rid of the radical. There. I divided the exponent by the root index. I divided this 12 by this 2. And then apply power to a power. So it's not any less work, not any more work. Same answer. It's just two different ways to get to the same thing, which is pretty neat. I mean, I think so, because I'm nerdy. But is it hard to read it? Is there a glare for you? No? Okay. It's hard for me to read it. When I look up there, there's a glare from the lights on the ceiling. Cool beans. Next. I'd like for you to look at your list of numbers. Is 128 a perfect cube? Nope, it's not. Shucks. I guess we're going to have to break it apart into something that is a perfect cube and something that is not. What perfect cube could I divide 128 by? (64). 64 will go into 128 twice. Now let's talk about A. Can I divide its exponent by 3 without a remainder? It's killing me that nobody's answering me. No, I can't. So what number could I have divided by 3, since I can't divide 19 by 3? Bigger. 18. You want the biggest possible one. You could have divided 18 by 3, and it would have left behind an a to the first. Can I divide b's exponent by the root index without a remainder? Okay, one person nodded, one person said yes. Of course you can. It's a 6. 6 divided by 3 is not going to leave a remainder. Tell you what will happen, though. That and that will be stuck inside my cube root. They cannot be reduced. And anything that can be reduced pops on out. So we go, fine. What is the cube root of 64? That's the square root of 64. 4. 64 is a really neat number. It is a perfect square and a perfect cube. It's pretty neat. It's also a perfect 6th power. It's 2 to the 6th. So it's 2 to the 6th, 4 to the 3rd, 8 to the 2nd. Isn't that neat? Anyway, the 2 is stuck. When the a comes out, what will its exponent be? 6, yeah, because you're dividing its exponent by the root index. This a is stuck. When this b comes out, what will its exponent be? 2, because you're dividing the exponent of 6 by the root index. And then it's times the cube root of the things that were stuck. There it is. Alrighty. Moving on. Is 16 a perfect 4th power? Yes, it is. It's on our list of 4th powers. But the 9 right here, I'm not going to be able to divide that by 4. If I tried, what would its remainder be? 1. That tells me I just need to break 1 off of it. What color? I need to use purple. We need to break one of our x's away. So that's going to leave us 8 of them. Well, we can clearly divide 8 by 2, so we don't need to do anything with the y's. What I'm seeing is a stuck thing. And the rest of it is liberated. 4th root of 16 is 2. When the x comes out, what will its exponent be? 2, because 8 divided by the index of 4 gives me 2. That's stuck. We've already said what happens when a power of 8 comes out. It comes out as a power of 2. Then we have a 4th root of x hanging around. I'm going to skip E. You need to see F before we leave. So hopefully you haven't packed up yet. Oh my goodness, a negative number inside a square root bar. What kind of result is that? I, an imaginary. All right, time to break this thing apart. There's a negative on the front, but whatever. What perfect square goes into 50? 25 does, so we're going to break it into negative 25 times 2. Do I need to break the m's apart, or can I divide its exponent by the index? You can divide, so I don't need to break them. Do I need to break the n's? Yes. How many need to break off? Just, well, 4 and 1. Now we just take square roots of stuff out. There's already a negative sign on the front. What is the square root of negative 25? 5i. Oh, you know what? That 2 is stuck and this n is stuck. When the m's come out, what is their exponent? 4, because 8 divided by the index of 2 gives me 4. When the n's come out, what is their power? 2, because 4 divided by the index of 2 is 2, times the square root of 2n. Woo, we almost didn't make it, nerds.